Hi everyone, my name is YuAng Chen. And, today I'm going to present my work called Groot, Graph-Centric Row Reordering with Tree for Sparse Matrix Multiplication on Tensor Core. This work is collaborated between CUHK and Hong Kong University of Science and Technology. So the design of Groot consists of three parts. I'm Groot, and I'm Groot. So anyone? My talk is over. Any questions? So joking aside, let's dive into the actual research. So I'm going to split my work into four parts. First, I'm going to introduce the background and motivation, and then the Groot design, and finally the evaluation. For the background, I'm going to briefly mention what is sparse matrix and how what is the correct features of the modern GPU architecture. Sparse matrices are everywhere in AI. For example, in the GNN, they represent irregular graph matrices. And also in the large language models, they come from the pruned or structured transformation. Optimizing in those sparse matrices is a key component for achieve better performance of the modern AI workloads. And specifically, we have two sparse matrices are mainly used in two kind of operation. One is the sparse matrix multiplication. The other is the sampled dense matrix multiplication. In the SPMM, one input operand is the sparse matrix, and the other sparse the other input matrix and the output matrix are the dense ones. For the SDMM, the two it consists of three input. The first and the second input are the dense matrix. Their results are then sampled by a sparse matrix, then outputting another sparse matrix. And importantly, both the SPMM and SDDMM can be parallelized row-wisely. This offers great insights for our following in exploration. Then I'm going to briefly mention the GPU. So the most used GPU is from NVIDIA, and NVIDIA's GPUs are specially designed, contains a special component called tensor cores, which are specially designed for the matrix multiply and add operations. This kind of hardware also can be found in Huawei's Cuba, Google, AMD, and Apple's accelerators. However, the tensor core can only handle the input and output matrices as dense, which are dense matrices. But in our previous sparse matrix multiplication, either the input or the output matrix is a sparse one. So with those background information, I'm going to further motivate our research. One way to bridge the gap between the sparse matrix and the dense tensor cores is the technique of graph condensing, which restructure the sparse matrix. These examples here shows the basic idea of graph condensing. You first partition as matrix A into row windows. Row windows are just a smaller rectangle matrix, and within each row windows, empty columns are removed. For example, those empty, this is an empty column, and it should be removed. Then the non-empty columns are shifted to the left side, like this, producing more condensed graphs. And finally, the condensed row windows are divided into non-empty blocks fitting into the sides of tensor cores. So those blocks can be well fitted into a tensor core for further computation. Then we observe that it is possible to reorder the computation row-wisely without infect the result. An example is offered here. In the second graph, we place the row 1, 4, row 0, 4, 7, and 6 together. Then after the reordering, we apply in the graph condensing technique to the reordered graphs, getting the final graphs. In the final graphs, we can find that there are only 2 blocks compared with the previous one. We have 3 blocks. And to optimize the graph condensing, to optimize the sparse matrix on tensor cores, there have already several studies focused on the reordering techniques to further speed up those sparse computation on tensor cores. In general, those approaches use the Jacob similarity to rearrange rows in the matrix. And the Jacob similarities is essentially the intersection of 2 vectors divided by the union of the vectors. And the larger the Jacob similarities, and the higher similarity between the 2 rows. And based on the Jacob similarities, those reordering approach use locality sensitivity hashing clustering algorithm to partition the matrix into row windows. In a matrix, rows with higher similarities are grouped together, and within each clusters, the rows are then placed to be in the same row windows. However, we found that existing row reordering algorithms are limited. Based on the Jacob similarities, we can find that for the row 0, it has only 3 similar rows with Jacob similarities with score greater than 0, which are 4, 1, and 7. And if we put in those rows together and then applying the graph condensing techniques onto the reordered rows, we will find that there are still 3 blocks left here, which means that there is no optimization. So I'll wrap up for our motivation is that we know that graph condensing technique can optimize the sparse matrix multiplication on tensor cores, and it is possible that an ideal graph reordering technique can enhance the effectiveness of the graph condensing, but the existing row reordering algorithms are ineffective. The reason for the ineffectiveness can be generalized in 3 parts. The first one is that the objectives are misaligned between the row reordering algorithm and the graph condensing techniques. The graph condensing techniques is designed to remove the empty columns, but the row reordering algorithms are designed to group similar rows. These 2 goals are actually mismatched. And the limitation of the cluster algorithm is also another important reason. the clustering focuses on the similarity between the cluster centers and the individual row, but the similarity of each row is more important. Also, the formed clusters typically differ in size, but the row windows has a fixed size. This means that the formed cluster should be requires further merging or division after the graph condensing, which determining the similarities. Last but not the least, the LSH method is not effective enough. It is a probabilistic hashing method that does not guarantee exact matches, and also multiple hash tables are required during the LSH algorithms, which increase not only memory usage but also computational time. So, to tackle those issues, we propose Groot. It is an approximation approach with detailed complexity analysis. The design principles for our methods consist of 4 aspects. First one is to align the matrices. Here we use the Hamming distance instead of the Jacob similarity to measure the difference between rows. Secondly, our goal is to minimize the row difference instead of the clustering the rows into groups. Also, we use graph-centric approximation algorithm to approach the optimal solution with a theory bound. And then lastly, we use a tree to decide the final ordering ID for each node, or for each row. So, to align the matrix, we formalize the row difference using the Hamming distance. Hamming distance essentially measures use the union of the set to minus the intersection of the sets. It can be interpreted as the count of mismatched elements, and it emphasizes the difference between the 2 vectors. Also, the ideal reordering objective of Groot is to minimize the total Hamming distance between the within and across the row windows. And in our paper, we offer the detailed analysis about the complexities, which turn out to be computationally infeasible because of the factoring. To simplify the problem, we're relaxing the original problem by removing the window-based constraint and focus on the minimizing the total Hamming distance between consecutive rows for the entire matrix. Hence, we redefine the row reordering problems as such that to find the permutation that minimizes the sum of the Hamming distance. However, this problem is still NP hard. It is equivalent to the traveling salesman problems, and the detailed proof is in our paper. And in short, the TSP problem is a salesman is that a salesman must find the shortest possible route that visits a set of cities exactly once. It forms a complete undirected graphs with n nodes and n sparse edges, which is essentially a dense matrix, and still too complicated to compute. To further simplify the computation, here we use we construct a KNN graphs that connect the rows based on the Hamming distance, and each row of the sparse matrix represents feature vectors. After that, we use the to obtain the near optimal row reordering. We further employ the minimal spanning tree based heuristic. The incorporation of MST is motivated by the effectiveness in approximating the TSP problem. And here specifically, we use the Kruskal algorithm with the strict optimization of path compression and multiple connected components. After that, we apply the pre-ordered DFS on the MST to obtain the final order. And this solution provides a two approximation for the TSP problems, ensuring that the total path is at most twice as the optimal solutions. So, to summarize the algorithm, the Groot consists of three steps. First one is to construct KNN graphs, then it extracts the MST from the KNN graphs, and finally perform the pre-ordered DFS on the MST. And for the complexity, the original problem, we relax it into a complete graphs. Then we apply the MST. We apply the KNN to extract the key component of the complete graphs, and finally obtain the MST. And the complexity of them is here, and the details can be found in the paper. We perform the performance evaluation on the tensor cores and as well as on the CUDA cores, and we use the LST and the TCM row reorder methods to benchmark. And the tested hardware is AMD CPU and NVIDIA GPUs. So for the tensor cores, Groot achieves average speedup of 1.8 times, and for the SDDMM on tensor cores, we achieve even higher speedups. And the contrast between and these pictures show that visualize the effectiveness of the graph structures on the algorithms. And it can be found that Groot reorganized the non-zero elements along the diagonals, and the condensed techniques further produce more concentrated and balanced non-zero distributions for the graphs. And we also measured the number of non-empty tiles reduced by the Groot. It shows that from 5 to 70% tiles are reduced, which directly translates to the number of MMA operations on the tensor cores. And finally, we apply Groot on GNN and found the speed up. Found 1.22 speed up for GCN and 1.38 speed up for the attention-based graph neural networks. Also, we applied the Groot on the weight matrix of large language models, and we see that when the sparsity x is below 50%, it does not produce any meaningful result. But when as the sparsity increase, we find we can see larger speed up especially at the sparsity of 99%, which is the normal sparsity of real world graphs. And finally, we want to summarize our contribution. We rethink the sparse matrix optimization for modern AI hardwares, though our work is algorithm, but its focus is mainly on the practical systems that bridge the sparse AI workloads and the modern AI hardwares. And the future work includes implement more efficient algorithms and better approximation algorithms than the existing MST. And the code is now available on GitHub. And if you have any further questions, you can ask me now or send me the email.